Welcome back to ECE 501B. If I had to entitle this lecture anything, it would be the orthogonalization lecture. We will be playing with this concept of orthonormal vectors, forming a basis with those vectors, and using those in very important ways, and we will continue to build on that even after this lecture. Just as a reminder for announcements, homework number 6 is due on Thursday, the 24th of October, and we will be back in the classroom on Wednesday, the 23rd of October, and I hope that this lecture works for you. Thank you for allowing me the flexibility to actually do this ahead of time, and maybe that will provide you with some flexibility in your schedule, at least at the early portion of this week. Again, this lecture, you could call it the orthogonalization lecture. I guess I just like to say that word. It's actually a mouthful and it's pretty long to write. But here are our goals that we want to try to get into for today. One is using this concept of an orthonormal list of vectors, we can actually use that to build or to create a particular expansion of any vector in a given vector space in terms of an orthonormal set of basis vectors. And that will then give us an orthonormal expansion of any vector we want in that vector space, let's say capital V. Obviously, then it's going to be important to be able to produce or create these orthonormal lists, and in particular, if we keep going, an orthonormal list that forms a basis, and that will be created by this Graham-Schmidt orthogonalization process, will show that that holds or is valid by a proof by construction, and because of that, that proof is pretty powerful. It actually allows us to build up a set of orthonormal basis vectors from a set of linearly independent basis vectors. Once we have this way of producing an orthonormal basis, then we can create a lot of different corollaries, and in particular we'll look at 4 of those. We'll simply state those. For more information, you can refer to your textbook. Then we will move into orthogonal projections. What does it mean if we can only live in a particular subspace within the original linear vector space? Then can we actually project a generic vector in the vector space onto that subspace that we can live on? And that will then provide us with this vector space direct sum decomposition. We can represent any vector as living in, let's say, this given subspace U and its orthogonal complement, which we will define. And so we can now subdivide any vector in terms of these 2 pieces, one in U and one piece in its orthogonal complement, and we'll call that U perp for U perpendicular. That will give us this vector space direct sum decomposition, and it might be nice to be able to project onto that subspace U, and that's what we will talk about or try to finish the lecture with, talking about the projection operator, capital P sub really capital U. To get us back on the same footing, let's just recap a little bit what we know or we've already covered in previous lectures, and that is a couple of propositions or a proposition and a corollary dealing with orthonormal lists. And again, these lists in proposition 615 is not necessarily of length the size of the dimension of our vector space capital V. It may be less, but it's a list. if e sub 1, e sub 2, and e sub m, these are m vectors in our vector space V, capital V, if that is an orthonormal list in V, and remember orthonormal means pairwise orthogonal, each of those vectors, and each vector has a length of 1, or it's a unit length, then we can find the norm squared of some linear combination of those orthonormal vectors as simply taking the scaling factor in front of each of those orthonormal vectors and find the magnitude or the absolute value of each of those and square those individual scaling amounts, add those up, and that will give us the norm squared of this, let's say, newly created vector V that might be represented by this linear combination a sub 1 e1 plus a sub 2 e sub 2, etc. And these a sub 1s through a sub m are any scalars in our field, let's say F, block F. And that upside down A, capital A, simply is a shorthand way of writing for all. That's proposition 615. If we can represent a vector, V, I don't necessarily need to call it V sub 1, maybe we just call it V, if it's now some linear combination of an orthonormal list in capital V, then we can find its norm squared rather easily. Immediately following out of that proposition is corollary 616, which says that every orthonormal list of vectors is linearly independent. And that follows, we proved that last time, because if we had a orthonormal list and we represent those vectors in that list as some linear combination of themselves, then it basically says that all of these coefficients must have to be 0, the a sub 1, a sub 2, a sub m, or these scaling factors, and that means that those particular vectors in that list, those orthonormal vectors, are linearly independent. Now that we have a list that's linearly independent and orthogonal, it's sort of begging us to extend that list from, let's say, M to the size or the length of the underlying dimension of our vector space, which we might say is little n. Or an orthonormal basis is an orthonormal list in our vector space, capital V, that is also a basis on V. And we know what it means to be a basis. We have to have vectors that are linearly independent, and they have to span the space, and they have to be, we have to have as many of those vectors as the dimension of our underlying space. We could then rewrite this orthonormal basis sentence as any orthonormal list in our underlying vector space, capital V. The length of that list, so of length, let's say dimension of V, that list then forms an orthonormal basis, or is an orthonormal basis. An orthonormal list says that we have these pairwise orthogonal vectors. They're of norm 1 And if we have enough of those, let's say dimension of capital V is little n, then if we have n of those vectors, we can create an orthonormal basis out of that orthonormal list. That follows because from some of our previous results, the previous result, which was corollary 616, shows that those vectors in that list are linearly independent. If it's an orthonormal list, then they're linearly independent, and that's one of the conditions of a basis. We need to have linearly independent vectors. And this linearly independent list, or set of vectors, and the fact that it is the correct length, which is equal to the dimension of the vector space capital V, the fact that it's a linearly independent list and of the correct length, then that implies that orthonormal list, it is a basis. We can now create or write down a theorem that's very helpful in terms of decomposing any vector in the vector space V. And that's a result of the fact that these orthonormal bases, they don't have to be unique. That's why it's BASES. They provide a lot of handy tools, or these orthonormal bases are very handy because it is easy to decompose vectors in terms of these bases, because remember, these bases are orthogonal. And so if you looked at each one pairwise, or each pair, they do not align. They're linearly independent of each other. And that provides us then with theorem 617. If E1, E2, up to E sub m is an orthonormal basis, on our linear vector space V, then we can conclude a couple of things. One is we can expand or decompose any vector V in terms of these basis vectors, these orthonormal basis vectors. We have the inner product of V with E1, or how much of this vector V is aligned with the first orthonormal basis E1. That will give us a value or a scalar. We'll scale then that basis vector E1 by that scalar. We will continue to do that with each of these orthonormal vectors. That will give us then an amount that vector V is aligned with each of those vectors, and that will then scale each of these orthonormal basis vectors, E sub 1, E sub 2, E sub m. We then can decompose any vector V in this way, and we can compute the norm of any vector then, the square of that norm, quite easily based on a previous result, and that is we take the absolute value of these scaling factors, and we were calling them a sub 1 for E1, a sub 2 for E2. We square each of those absolute values, and add them up, and that's going to give us the square of the norm of the basis v. Again, this is true for every vector v that lives in our vector space capital V. That's a powerful theorem. Let's prove that so that we are comfortable accepting it and working with it. First, let's simply write in generic terms or in general terms an expansion of our vector little v. We're used to writing v as some linear combination of basis vectors, and we maybe called those a sub 1, a sub 2, up to a sub m, where we have m of these basis vectors, e1 through e sub m. Now that we have v parameterized or decomposed in terms of these vectors, let's now form the inner product of that vector v with each of these orthonormal basis vectors individually. Let's now form the inner product initially with just the first one, e sub 1. Let's form the inner product with e1. We take v inner product with e1. Well, that's just going to be a1 e1 plus a sub 2 e sub 2 based on this decomposition of v in terms of these orthonormal basis vectors e1 through e sub m, inner product with e sub 1. And we know how that first argument then, or the additive property of the first argument or the first slot in the inner product works. We can then rewrite this as m such inner products. We can say, oh, that's a1 e1 with e1 plus the inner product of a2 e2 with e1, and so on down to the inner product of a sub m e sub m with e sub 1. And I'll skip the step of homogeneity in the first slot, but each of those scalars, a1 through a sub m, can slide outside of that inner product and simply scale the resulting inner product. And we then have the inner products, or what I'm saying, maybe I won't skip it, is we now have the following expression. But knowing now what we know about these orthonormal vectors, the only one that is going to be non-zero is the inner product of the orthonormal vector with itself. By definition, how we've defined those vectors. Consequently, we have a1 plus 0 plus all the way up to another 0, or the inner product of v, any vector v, with e1 is simply going to give us this coefficient a sub 1 if we've decomposed or rewritten v in terms of a linear combination of these orthonormal vectors e1 through e sub m. And hopefully then it's clear that we can just step through or repeat that process of forming these inner products for each of these basis vectors e2 up to e sub m. We'll repeat for all other vectors in that list of orthonormal list of basis vectors. And I hope it's clear then that the inner product doing that, let's say with e sub k, returns a sub k. Or we can say that v with e1 is going to be a1, v with orthonormal vector e sub 2 is a sub 2, and that just continues down to this scalar coefficient a sub m equaling the inner product of v with the orthonormal vector e sub m. That says then that v is now a1, but we've now learned that a1 is simply the inner product of v with e1 that scales e1. A sub 2 is simply the inner product of v with the orthonormal vector e sub 2, etc., all the way down to v inner product with e sub m, scaling e sub m. That's then the first half of the proof, which was that we can rewrite any vector v in our vector space capital V as a linear combination of the orthonormal vectors or orthonormal basis, and the coefficients or the scaling factor associated with each of those basis vectors is going to be given to us by the inner product of the original vector v with the orthonormal basis vector e1, e2, etc. The second result, I hope it jumps out that that's simply proposition 615, and so we won't prove that. I'll just say that the second half of the theorem which was theorem 617, follows directly from proposition 615. And that then completes the proof. If you've played with Fourier series, hopefully you see the connection. And if you don't, maybe you should go back to the Fourier series discussion that maybe you have played with and see that, well, if we were taking a junior level class here at the University of Arizona, we might see that the exponential Fourier series coefficients, capital C sub n, might be this 1 over t, t being the period of our periodic waveform, and then we integrate over any period interval, capital T, where now we're trying to find the Fourier series expansion of a periodic waveform, capital F of t. We simply take the inner product of f of t with this complex exponential, which really is an orthonormal basis vector, e to the minus j n omega, let's say t, or omega naught t dt. Meaning this is now an orthonormal basis vector, and n omega naught, whatever n is, gives us a new orthonormal basis vector, and this integral is now the inner product, and that provides us with these coefficients that then scale each of these orthonormal basis vectors in, let's say, an exponential Fourier series expansion. That's then a connection of a concept that we've derived for these finite dimensional vector spaces. We could extend that to an infinite dimensional vector space by means of this Fourier series example. Now, we can see then, or let's say, okay, I believe that this concept of the orthonormal basis are useful, but I'm a little unclear as to how to come up with an orthonormal basis set or a list of orthonormal. And that's what the next procedure is going to allow us to do. Okay, an orthonormal basis, they are very useful, but how do we generate, or how do we go about finding these orthonormal lists, which we create then or build up to become an orthonormal basis? How do we go about finding these orthonormal bases? And that's where the Graham-Schmidt orthogonalization process comes in. In the textbook, that's now we're down to line 20 in chapter 6. Here is the orthogonalization process known as the Graham-Schmidt orthogonalization. If we take a linearly independent list of vectors, v1, v2, up to, let's say, v sub m, if that list is a linearly independent list of vectors in our underlying vector space, capital V, then there exists an orthonormal list E1, E2 up to E sub m, where that new orthonormal list, E1 through E sub m, has the same span as our underlying list, V sub 1, V sub 2, or our beginning list of linearly independent vectors, where the span of vector v1, v2 up to, let's say, v sub j minus 1. Well, let's not do that. I'm getting ahead of myself and already trying to get into the proof. Let's just go up to v sub j is the same as the span produced by the orthonormal list of vectors up to e sub j. And this is true as we step through or build up from V1, we go to E1, V2, we go to E1, E2. This is true for all j up to the final value on our index of that linearly independent list, which was little n. Let's now prove that. And the proof is actually going to be an inductive proof, but it will also be a proof by construction. First, let's just assume that we have this list that's of length m of linearly independent vectors. So let v1, v2 through v sub m be a linearly independent list in our vector space capital V. We can then say, okay, the base case, which is, let's say, little l equal to 1, we can now let E1 equal V1 over the norm of V1. And I hope it's clear, all that over the norm of V1, that's just a scaling factor. The direction is still preserved between E1 and V1, which says then that the span of E1, I hope it's clear, is equivalent to or equal to the span of V1. And I hope you can convince yourself that E1 has a norm of 1. And as an exercise, you might just show that. Find the inner product of E1 with itself and convince yourself that you end up with that inner product equaling 1. And 1 squared, since the inner product with itself usually gives you the vector norm squared, but 1 squared is 1, so if the inner product is 1, you've got it done. That's the base case. Then we can step through by induction, and so we have to take our induction hypothesis, which is to go ahead and assume that this is true for values of j up to, let's say, j minus 1. Let's then assume that we're dealing with a j value bigger than 1. So now we've moved beyond the base case. And E1, E2, we've now built up a list of length j minus 1. And then for this hypothesis to be consistent with our base case, then we want this list of j minus 1 vectors to have the same span as the list of linearly independent vectors v sub 1 through v sub j sub 1, where the span of v1, v2, v sub j minus 1 is equal to the span of E1, E sub 2, E sub j minus 1. Now we can continue. Now we want to sort of break it up into two pieces. Let's look at the jth step. Omega sub j, let's say, is v sub j, the jth linearly independent vector. But now we want to remove from that pieces that are already aligned with the previous orthonormal vectors E1 through E sub j minus 1. And we can do that by taking the component of V sub j that's aligned with E1, and we can do that by forming the inner product of V sub j with E1. And then that's the scaling amount that weights E sub 1. We take V sub j and form the inner product with E sub 2, and we just continue to do that until we reach V sub j inner product with E sub j minus 1, and we scale that, or use that to scale E sub j minus 1. What we're doing then is we're actually pulling off pieces or component parts of V sub j. In this process, then, we are subtracting off, or this process subtracts off, all parts of, let's say, V sub j that are in line with or are along the different E sub L's, where these E sub L's are coming to us from E1, E2, up to E sub j minus 1. Now, remember that V sub j is linearly independent from V1, V2, up through V sub j minus 1. So even though we're subtracting off what seems to be a lot of information from V sub j, we still have a little bit left because V sub j is linearly independent of all these other vectors in the orthonormal basis list, E1, E2, E sub j minus 1, that precede V sub j. Or, what I'm trying to say is something must be left, or left over, since the V sub j's are linearly independent. Or maybe I should call it something else since we're kind of playing with V sub j. Maybe I say all of these V sub i's are linearly independent. And what's left over is actually perpendicular, so I'll use this symbol, the perpendicular symbol. The remainder, what's left over, is perpendicular to all of these orthonormal vectors, E sub i's, that are contained in E1, E2, up to E sub j minus 1. So now we've created a new vector, W sub j, that only has left as a part of it a component or component that's orthogonal to all the previous orthonormal vectors E1 through E sub j minus 1. That W sub j, though, we're not guaranteed that that's going to have the length that we want. We want these vectors that we're building up, these E sub 1's, E sub 2's, to be normalized to have a length of 1, and that's not too difficult to achieve. Once we have the vector, we can now let E sub j simply be the vector W sub j divided by its norm. And that normalizes E sub j to have a length of 1. All we've done is scale W sub j, meaning W sub j and E sub j are in the same direction, or E sub j is the same direction as W sub j, and E sub j is perpendicular to all the preceding E sub j's. And because we've divided W sub j by its norm, we now know E sub j has a norm of 1. If we now take those two steps as a whole, 1 and 2 together, now imply that V sub j is now in the span of E1, E2 up to E sub j, and consequently then the span of V1, V2, V sub j is contained in the span of E1, E2, E sub j. And these lists, V1 through V sub m, E1 through E sub m, both of those lists are linearly independent. And because at each step you're adding one more component onto it, the amount of components you have equals the number of vectors in your list. So both lists are the same dimension. And that dimension in this example of going up to j is of length j. So both lists or both lists have dimension. Maybe I should say it that way. Both lists have dimension of j. Which means that since the span of those two are consistent and they have the same dimension, then those subspaces are the same. And we can then say that those spans are in fact equal. And that's what we needed to show for our inductive process to work. We needed to show that indeed we continue to be linearly independent and we grow with each step, and we went up to the jth step in our induction hypothesis, and that was actually a proof by construction, and that's then a pretty powerful, this theorem is pretty powerful. And its proof was by construction. And that's one of the things that makes it powerful, which says that we not only know that it's possible to create these orthonormal lists using the Gram-Schmidt procedure or the Gram-Schmidt orthogonalization procedure, but we also have a way of constructing that list. So it was a proof by construction, which says that we not only know it's possible to build such a list, we know how to construct the orthonormal basis. And once we have that, now we have a very good set of corollaries. And let me just sort of rattle those off. So we now have a number, or list those, a number of useful results are possible. And you can refer to the textbook or to Axler for the details. first is corollary 624, which says that every, and I'm going to use some abbreviations here, every finite dimensional IPS, or inner product space, given a finite dimensional inner product space, that inner product space, finite dimensional, has an orthonormal basis. That's nice to know. So if you give me a finite dimensional inner product space, we can find an orthonormal basis. You give me that space, maybe I can find a set of linearly independent vectors, and now with the Gram-Schmidt orthogonalization process, I can turn that that linearly independent list into an orthonormal basis list. Another corollary, corollary 625. Every orthonormal list in our vector space V. So we might start out with an orthonormal list that's not quite complete in that it may not be as large, or the length of our dimension of our vector space V. Well, we can complete that list to make it a basis. That's corollary 625. Every orthonormal list in V can be extended to an orthonormal basis on our vector space V. And that just means we need to grow our beginning orthonormal list by augmenting it with some linearly independent vectors, and then with the Gram-Schmidt orthogonalization process, orthonormalize that set of linearly independent vectors. The next result that follows from the Gram-Schmidt orthogonalization process is if we're given a linear operator, let's say capital T, and it's a linear operator on a linear vector space capital V, if that linear operator T has an upper triangular representation, so now we've put it into some matrix form, the linear operator. If T has an upper triangular representation with respect to some basis on our linear vector space V, then that operator T actually has an upper triangular representation with respect to an orthonormal basis on V. Meaning we don't have to have our set of basis vectors not as an orthonormal list. We can produce a upper triangular representation of that linear operator with a orthonormal basis. And that orthonormal basis can be created from the Gram-Schmidt process applied to the original basis. So the orthonormal basis is just the Gram-Schmidt orthogonalization process on the original, maybe it wasn't orthonormal, but it was a basis, we can now create an orthonormal basis using the Gram-Schmidt approach. So that Gram-Schmidt approach is very powerful. One more corollary before we move into some more results, but that Gram-Schmidt provides us with a lot. Now we've created or written down 4 more corollaries. If we're now given a linear vector space V that's finite dimensional and it's on a complex inner product space, so given this finite dimensional complex inner product space and a linear operator T on that finite dimensional complex inner product space, then that linear operator T has an upper triangular representation with respect to, I think you already can guess where I'm going with this, with respect to some orthonormal basis. That's the Gram-Schmidt. Now that we have this ability to create orthonormal basis sets, now we can start, because they are orthonormal, we can start looking at things that are orthogonal to one another, and in particular, this concept of orthogonal projection. We can now project from the overall space V into some subspace that is orthogonal to these vectors V. So here is an orthogonal projection. Given U, and U at this point in the discussion is not necessarily a subspace. Let's just let it be a subset of V. So now we have some collection of vectors that form a subspace, or I'm sorry, a subset of our linear vector space V. From that subset of vectors, we can define actually what will turn out to be a subspace, but we can define the orthogonal complement of that subset U. And we will give that orthogonal complement maybe an easier description. We will call it U perp, and we'll just say that that's U with a subscript of that perpendicular symbol. So U perp, which is called U perp for this subspace that's perpendicular to U. So for U perpendicular, U perp is then U perp, let's see, we can define the orthogonal complement of U. U perp is the set of all vectors in V, the linear subspace, that are orthogonal to all of these vectors in the original subset, capital U. The notation that we will use then for U perp is to say that U perp is this set of vectors that are coming from our original vector space V, such that if we form the inner product with V and U, where U is now, let's say, for all U in our subset of vectors, capital U. So that the vectors in U perp are orthogonal to all the vectors in the subset, capital U. Now that you have some mathematical maturity for after this first 7 weeks or whatever it is we are into the semester, now we can start using some of these quick phrases. It should be obvious, and I'll put obvious in quotes because we may want to convince ourselves why it's so obvious, but it should be obvious that this U perp is actually a subspace even though the U that we started with wasn't a subspace, it was actually just a subset in general. U was a subset, or not necessarily a subspace. And what's it take to be a subspace? Well, we need to make sure that our subspace contains the zero element or the zero vector, and that vectors in that set, when we form linear combinations of vectors in that set, we need to remain in that set, or the set is closed. And let's then just sort of try to argue that. The only part of our vector space V that isn't in U perp are actually those vectors that are perpendicular to all vectors in U perp. That's by construction of U perp, which says that we can't get to those vectors that are perpendicular to the vectors in U perp. We can't get to them. And one way you could maybe think of that, the vectors in V minus U perp through addition or scalar multiplication of vectors in U perp, which says that U perp is in fact closed under arbitrary linear combinations in U perp. Also, not only is it closed under linear combinations, but the zero vector, by definition, is perpendicular to everything. We talked about that when we were discussing our inner products. The zero vector is perpendicular to everything, and consequently then, so the zero element is also in U perp. So U perp contains the zero element, and any vector or linear combination of vectors in U perp remain in U perp, so U perp is a subspace. Now let's look at what comes together for us if, in fact, we look at the case where U, what we begin with, is indeed a subspace, and that's theorem 629. If this first thing that we start with, capital U, is not only a subset, but it's also a subspace, so it has to contain the zero vector or zero element, and it needs to be closed under vector addition and scalar multiplication. Then we can actually create this or decompose our linear vector space V as a direct sum decomposition of the subspace U and U perp or its orthogonal complement. Likewise, we can come up with a corollary, 633, that basically says if U is a subspace, then we can also say that if we take the orthogonal complement of U and take the orthogonal complement of that, we will actually get back to our original subspace U. So the perp of U perp is U. Those are some interesting theorems and corollaries that now will allow us to do even more powerful constructions. Let's look at some examples. Suppose that we look at our original linear vector space is the two-dimensional plane, is R2, and it's real. Suppose we now let U be the x-axis. What's U perp? The orthogonal complement to the x-axis in the plane is actually the y-axis, isn't it? And what can we conclude from that? Well, we can actually conclude the earlier theorem, theorem 629, and corollary 633, meaning if we start with the x-axis, then the direct sum decomposition of the x-axis with the y-axis, or U perp, gets us all of R2. And that's what theorem 629 stated. What about if we start with the x-axis and we take its orthogonal complement, then we get the y-axis. If we take the orthogonal complement of the y-axis, we get back to the x-axis, and so in fact, both the theorem and the corollary for that example, example 2, where our original subset U was the subset was a subspace, which was the x-axis, then we find its orthogonal complement to be the y-axis, then those two theorem and corollaries are valid. What if we looked at something that wasn't quite the same? Suppose we start with the same underlying vector space, R2, but now suppose that we just let U be some subset of that. Let's say it's just the vector 3, 0. So just realize that now we're saying that U is not the same as the span of this vector 3, 0. If it was the span of 3, 0, then that would be the x-axis. So right now, let's just say that it's a vector in the x direction. What's U perp? Well, what vectors are in the orthogonal complement to this one vector in the x-axis or on the x-axis? We now get the y-axis. But if you now looked at just this single vector 3, 0 with the y-axis, hopefully it's clear that we do not get the space back when we take the direct sum of this vector 3, 0 with the y-axis. We can't build everything up out of that combination. Mainly U is not really even a subspace, so this direct sum doesn't make any sense. And if we take this vector 0, 3 and we find its orthogonal complement, then we get y. We find the orthogonal complement of the y-axis, which is the x-axis. That's not equal to just that single vector U. Let's now continue with this situation where U is indeed a subspace. In the case, since that's going to give us a lot more power to play with, let's let U, or take the case where U is a subspace. The direct sum representation of V of our linear vector space implies there is a unique, remember what the direct sum decomposition allowed us to do. Now we can take vectors from the individual subspaces making up the direct sum decomposition. The direct sum representation of our linear vector space V implies there is a unique decomposition of all vectors in our linear vector space V in terms of elements in these orthogonal subspaces. What does that mean? That means then that for all vectors V in our original linear vector space, capital V, little v can be separated into two pieces. One piece, little u, is coming to us from the subspace capital U, and W is actually coming from the orthogonal complement of U. And now we have a vector V written in terms of two pieces that are orthogonal pieces to each other. And that's powerful. That allows us then, we use this to define this concept of this direct sum decomposition. We use this to define a projection operator, which we will then denote, and that's supposed to be capital P sub capital U. What this is this is the orthogonal projection of any vector in V, so we'll just say of V, onto the subspace U. So now for all vectors little v in capital V, now we're saying V is equal to U plus W, or we can decompose V into two pieces. U again is in the subspace U, and W is an element of the orthogonal complement, or U perp. Then for all V, little v, we can define the projection operator P sub U of V will just be the piece of V, or the component of the vector V, that lies in the subspace U, with little u an element of capital U. And once we have that, then we can establish actually quite a few properties of the projection operator. And remember that what we mean by an operator, it maps from the original vector space back into itself. Well, it should be clear that the projection operator P sub U is an operator. So it's a linear operator on V, and in particular it actually keeps everything in the subspace U. So here are some of the properties of the projection operator. One is that the range of P sub U is all of the subspace U. A second property is that the null space of this projection operator, again this is an operator, so it's a map, a linear map from U back into U. The null space, those vectors that actually get taken to the zero vector through this projection operator, those vectors lie in U perp. We also know that if we take the original vector V, any vector in our linear vector space, and take off the component that lives in U, and we've maybe been calling this W, that component is actually in U perp. Another property, so we're listing a lot of properties, but these are very powerful properties. If we take the projection into U twice, that really doesn't do anything more than already what we did if we projected onto U one time, because the projection operator really just lives within U, the vectors, once it maps them down. The other is that the norm of a vector once it's projected into U must be less than or equal to the original norm of that vector for all v in V. And let's conclude then with one more very, very powerful result when we have these projection operators. Suppose that we can create an orthonormal basis on the subspace capital U. So also we can use an earlier result which says that if we have an orthonormal list of vectors e sub 1 through e sub m, and in fact that list forms an orthonormal basis on U, meaning it spans all of U and its dimension or the length of this list is equal to the dimension of our subspace U. So if this set of vectors, e sub 1 through e sub m, is an orthonormal basis on U, then if we take the projection operator of any vector v, then that would be provided to us, or we can do that by simply taking the inner product of the vector v, any vector v in our overall vector space capital V, and scale the orthonormal vector E1 with that scalar amount, v inner product with E1, plus v inner product with E2 scales E2, and we continue that process until we get down to the final orthonormal vector E sub m scaling E sub m. That is now result 35, or line 35 in the chapter 6 of our textbook, and that's a very powerful result that actually says now we can actually project any vector v in our overall vector space, capital V, onto the subspace U if we have an orthonormal basis on U. And we'll pick up at that point next time, and this now allows us actually to begin to look at minimization problems, which is a very, very powerful technique that's applied in many different disciplines.